Hey everyone. So for the next session, Simon, Chien-Chin, and I will be talking about Torch.Compile for Autograd, DDP, and FSDP. So I'll give it to Simon.
Hi, my name is Simon. I work on the PyTorch team at Meta. And I want to talk to you guys about, first, ease you into the topic of distributed training by talking about how Torch.Compile interacts with the Autograd system today on a single GPU level. So tensors that require gradient keep track of their history. Anytime you execute an operation in the forward pass, there's a state that is being kept, and we'll call that the Autograd graph. So every single operation in the forwards pass has an equivalent node in the Autograd graph that corresponds to its derivative implementation. So as you can see, we run an add, and you should see an add backward correspondent. If you run a sum, you should see another node. And when you begin the backpropagation step by calling .backwards, the C++ Autograd engine will take this graph and it'll execute the operations in reverse order. This is what we call reverse mode automatic differentiation. So let's talk about Torch.Compile. Let's say we wrapped what we had earlier that ran in eager, the 3 ops, in Torch.Compile. And there's no graph breaks in this case. You'll notice that in the Autograd graph representation, there's actually only a single node installed. And this node corresponds to the optimized backward that Torch.Compile has traced ahead of time. And you'll note that this is actually not the entirety of the Autograd graph. And in fact, only the portions that I've circled in red today are the portions of Autograd that are visible to the compiler. And everything else would run in eager. So you can already see there's some other nodes in this Autograd graph that are running in eager. And there could be potentially other things that the C++ Autograd engine is executing that is not being stored as part of these graph nodes. So I want to talk about these portions, because these are the limitations of Torch.Compile and Autograd today. So the first one you see are the accumulate gradient nodes. So these nodes decide the logic on how you set the gradients of the tensors that require gradient. And this is the implementation, depending on the gradient, can issue different types of ops, like detach, sum, clone, and all of these would be running in eager. And you have one of these per input tensor parameter. So let's say you have a linear layer, well, that'd be 2 accumulate grad nodes already, one for the weight and one for the bias. The second portion that might be running in eager are backward hooks, if there's any in your program. And this happens to be a very popular place for people to insert their distributed collectives, because it's a way to add distributedness to your model without changing your model code. So if you have a model that you want to swap between eager for debugging and compiled plus distributed, like the hooks might be a good place. But the issue is the hooks do not exist inside the nodes. So Torch.Compile actually does not see into these hooks, and so we can't really compile them. It also means that in the compiled Autograd graph today that you would see, the compiler doesn't actually know about the collectives. So you're actually optimizing your compute and your communication separately, and it becomes very hard to perform good overlap. A third portion is if you have any graph breaks in your forward, Torch.Compile today traces ahead of time. So it'll trace a backwards corresponding of each forward graph. So you would get these graph breaks in your backward. But this isn't always necessary. Because the Autograd graph is mostly just a straight line of operations, and we shouldn't need a graph break. So this is why I want to talk about Compiled Autograd. It's something that we've secretly released as part of 2.4, and currently still in beta. So we're adding an additional pass for the compiler to trace at backward runtime. So what we do is we override the eager Autograd engine that would be executing the Autograd graph. We shadow run every single operation that the eager Autograd engine would have ran. And while we do that, we add them into a graph, the same as Torch.Compile, so an FX graph. And here you can see, on the sample example that I had before, I added some hooks to it. In green are the sections that we had already captured in the ahead-of-time trace of the backwards. And in red and blue are the additional sections that are captured when you enable Compiled Autograd. So the API for Compiled Autograd today is still gated behind an API. You turn on a config, and then it will override the Autograd engine for anything, for any backward call that happens within a Torch.Compiled function. So there are still some tracing challenges as of 2.5. So C++ user callables are one of them. Another one is the eager regions activation checkpointing. What these two extension points have in common is they usually operate a lot on non-tensors, and these are likely to cause troubles with us. So we got a larger graph. Now, does it always guarantee a larger performance, better performance? So the sad reality is that a lot of these larger graphs often don't come for free. There's a lot of variable overhead that comes with this. So in each iteration of the backwards, the compiler would need to extract all the inputs for this graph. It'll need to perform all the cache lookups and even safety assertions. So all of these scale with the size of the graph. So when it comes to ask, would this actually improve the performance, then you have to ask yourself a few questions. First is whether at the end of the forward pass, is the GPU still busy? Does it have leftover compute that you can hide this overhead from? And the other one is, if your model did have a lot of hooks and other eager compute, can the compiler make use of this extra compute in a way that it overshadows the overhead costs? We ran it. We basically blindly applied it to all the 160 OSS models that we use to benchmark Torch.Compile. And these models characteristically usually have very few eager compute left, few hooks. It was mostly a measure to see how affected are we still by this overhead problem. And we see that we are actually faster for 2/3 of the models, but we're still, overhead still dominates for 1/3 of them. The performance chart that you see here is compiled with regular Torch.Compile without compiled Autograd. So on the left-hand side, you can see there's some very few models that actually have a lot of graph breaks, in which case compiled Autograd would let you get a larger graph and better fusions. So in this case, we could see improvements of up to 21% compared to regular Torch.Compile. And on the other hand, on other models that would not have any eager compute left, then you're actually just paying for overhead for no reason, in which case we see regressions of up to 12%. So to recap, Compiled Autograd is a way to trace all the ops in the backwards, and you mainly want to use it for graph capture. There are certain situations that it's good for performance, and the third reason may be that if you want to use the new compositions with our distributed frameworks. I'll pass it to Chien-Chin to talk about Compiled DDP.
Hi, my name is Chien-Chin from PyTorch Distributed team, and thank you for Simon this great introduction to Compiled Autograd. Next, Will and I are going to discuss the use case of Compiled Autograd. So the first one is DDP, the simple one, and I'm going to give a 10-second introduction to DDP. Assume everyone here knows DDP at least. So DDP parallelizes the data by partitioning the global batch and into several mini batches, and each rank will take one small batch and train with the same parameters. But the gradient will be different, so DDP also needs to reduce the gradient by using O-reduce. So now the question is, can we compile DDP? In order to answer this question, we need to first understand the current implementation of DDP. So DDP utilizes PyTorch's gradient hook, which if you pay attention to what Simon just spoke is the like autograd, like the accumulator gradient hook. So DDP use this gradient hook because DDP needs to understand when the gradient is ready. And then DDP can issue O-reduce to reduce the gradient. There's also another logic is DDP does not issue one O-reduce per gradient hook. Instead, DDP wait until there are enough gradient and issue just one O-reduce for all these gradient. This can actually improve the communication efficiency. And all this logic is written in C++ reducer. So you might already notice there are two problems here. The first one is this gradient hook is not traceable by the original compiler without compiled Autograd. And also this C++ reducer, we can only know it happened, and the compiler cannot trace the logic inside this reducer. So what compiler can do is to actually compile the backward and execute the backward, and then execute all the gradient hook after the backward is finished. So unlike this figure, which we can essentially run in the backward and also issue the O-reduce, which can overlap the communication with some backward computation, with compiler, we actually cannot overlap the communication with computation. So in order to solve this problem, we actually propose and introduce a DDP optimizer. So DDP optimizer intentionally break the model. And now, instead of just getting one backward graph, you will get multiple backward graphs. And each backward graph will has exactly one O reduce. So now we can execute this backward graph one by one, and the O reduce for this backward graph can then be overlapped with the next backward graph. So that's perfect, right? Now we have the communication and the computation overlap. We also can compile the backward. However, there's one issue. DDP optimizer actually couple the DDP O-reduce bucketing logic with graph break. Imagine you just want to add a few linear layers to your model. And suppose Torch Dynamo should be able to compile this linear layer. But because DDP optimizer actually couple the O-reduce bucketing logic with the graph break, so you might get one extra graph because of these extra linear layers. This is not ideal. And the Compiled Autograd can actually save here. So we propose new Compiled DDP, and this new Compiled DDP essentially use Compiled Autograd to trace through the gradient hook. But we only solve one problem, like we now know what's going on inside the gradient hook. We still cannot trace through the C++ reducer. So this new Compiled DDP actually deactivate the C++ reducer and implement a very simple Python level reducer, which issue one O-reduce per gradient hook. But I just said that because there will be a lot of O-reduce if we don't do bucketing, then the communication efficiency will be bad. So we also implement a bucketing logic inside the torch inductor, which at that pace, we already have the full graph of the backward. So we can actually do the O-reduce bucketing easily inside torch inductor. So to recap, we propose new Compiled DDP and utilize Compiled Autograd to trace the gradient hook. And it issue one O-reduce per gradient hook. And we also implement O-reduce bucketing logic inside torch inductor. So what are the benefits of this new Compiled DDP? First of all, definitely we already explained, we kind of decouple the bucketing logic from the graph break. So we can get a one graph, and it actually enable more potential fusion. And one benefit I didn't write in a slide is the original eager DDP actually require user to specify that whether there are some unused parameters or if the execution is going to change during the training. And the user needs to understand this and write it into DDP's argument. But now with a new Compiled DDP, we get this for free because Torch Compiler and Torch Dynamo and also Compiled Autograd will understand this change if the execution order change or like there are some unused parameter and generate a new graph and pass to Compiled DDP. And next, we are going to discuss FSDP.
Thank you, Chien-Chin. So next, I'm going to talk about Compiled FSDP. So I think it's worth talking about what is FSDP. So as you already know, DDP needs to keep all the model weights on each GPU at all times. So the problem of DDP is that it can cause high memory usage if your model is very big. So FSDP was created to address this problem. So I have a flow chart here. So the idea is that before the model forward compute happens, each GPU actually doesn't have the full weight of the model. It has just a shard of the weight, which is one over n instead of 1. So on each GPU, the amount of weight would be smaller. And then when we need to do the forward compute for the model, we'll first issue the all gather to all gather the full weight for onto each GPU so that we can do the forward compute. And similarly, in the backward pass, when we need to do the backward compute for the models, we will first need to do the all gather to gather the full weight onto each GPU, and then do the backward compute. And then after that, we'll do the reduce scatter to synchronize the gradients for the model shot on each GPU. So FSDP right now is like the most commonly used parallelism techniques for large model training, including LLMs. Currently, when we apply Torch.Compile to FSDP, what happens is that for the communication operations like all gather and reduce scatter, which is like in the red boxes here, are run in eager mode. And then we only run the forward and backward compute in compile. The reason is that in the current enablement, we cannot trace into the communication ops, and then we can only trace into compute ops. The problem is that this prevents fusion at the graph break boundaries, and it also prevents full graph optimization where we can optimize compute and communication together. The North Star that we are working towards is full graph optimization, which means that all of the operations, including communication and compute, will be in one graph. There will be no graph break within the FSDP region. The benefits are, with the full graph, we can do auto-bucketing, we can do memory-based prefetching, and then we can do joint graph optimizations. The challenge is that we need to figure out how to capture the FSDP communication ops into the graph. So before we go into how we tackle the challenges, it's important to call out that for Compiled FSDP, we currently focus on FSDP2. So FSDP2 is like improvement over FSDP1, which adds support for flexible FPA all-gather. And this is important for FPA map-mount computation, which is like a very commonly used technique for compute speed-ups for the latest generation of GPUs. We focus on FSDP2 because it's easier to make Torch.Compile related changes to the new API. And we also want to advocate adoption of FSDP2 because it's simpler and better. So we go into how we trace FSDP2. So there are two main challenges in tracing FSDP2. One is that how we can support the various types of hooks that's being used in the eager FSDP2. So the hooks are used to run the FSDP2 communication ops at the right time. Those include like tensor backward hooks, module hooks, and the Autograd engine forward final callback hooks. So luckily, we have Compiled Autograd, so we can support all of that with Compiled Autograd. And the second tricky thing in FSDP2 is that there is an unsharded parameters resize pattern, which is there to try to make eager path performant, but it makes the compiled path a little bit hard to trace. So we iterate a lot on this design, and then we find a way to not have too much, just have a very little divergence, but allow us to have very simplified compilation graph. So let's talk about the optimizations that we can do once we have the full graph. The first one is auto-bucketing. So the idea of bucketing is that the bucket is trying to decide which parameters to participate in the same all-gather communication. The idea of auto-bucketing is that we can automatically discover the best bucketing to maximize the communication and computation overlap. For example, here, if we have a model that has 3 layers, like L1, L2, and L3, and then if we just naively apply FSDP on the top of the model, we will then run the all-gather at the beginning of the forward. And then after the all-gather is finished, we'll run the compute for all those layers. As you can see, this will expose the entirety of the all-gather operation on the GPU trace. Now, one easy thing that we can do is to do per-layer bucketing, which is that we just apply fully shard, which is FSDP2's API, on each of the layers. This will achieve some overlap, which help us save some training time. But if with a compiler, we can then go into layer 1 and find out that layer 1 is actually a combination of layer 1A and layer 1B, and then we can very granularly find out the optimal wrapping to optimize for the communication overlap. The idea here is that with the auto-bucketing, humans no longer need to manually fine-tune to find the best bucketing policy, and then also will save training time. The second optimization is memory-based prefetching. So on the top left corner here is the normal forward-backward memory usage of FSDP. As you can see, the green triangle here are the memory usage when we need to do all gather. But if we look at this model in more detail and look at the GPU trace, maybe we can run the all gather L1 sooner so that it can overlap with backward layer 3. The downside is that we'll have two all gathers in flight, the AGL2 and AGL1, which will mean there are higher memory usage at that point. But we also find out that the peak memory doesn't increase because of this reordering. And we'll also find out that this actually saves training time, as we can see here. The third optimization is joint graph optimization. So here at the top, we have a GPU trace, and then we have the orange area, which is the exposed communication for the all gather L3. We need this all gather because we don't save the output of the all gather in the forward pass for this layer specifically. But if after studying the model, we decide that it's okay to have a little bit higher peak memory to trade off for performance, we can save the all gather output for layer 3 in the forward pass, which results in higher peak memory. But then we don't need to run the all gather L3 in a backward pass, which saves training time overall. So this is also another kind of optimization that's uniquely enabled by joint graph. So what's available right now, we have a functional prototype of the compiled full graph FSDP2. And looking ahead, we are planning to add 2D parallelism and the mentioned performance optimization passes and the peak memory optimization passes. We'll also support having graph breaks in the forward pass of the FSDP2. And here, having graph break in the forward pass doesn't mean having graph break in the backward pass. So it will still allow us to have graph-based optimization in the backward graph. And we also work on compile time reduction, and then we'll also work on compiled 3D parallelism. And in general, we want to work on more automation and optimization in distributed training. That's it. Thank you.